Okay then, so let's continue with the next topic on VLSI circuits and design, static CMOS logic. So let's go into it. Okay, so for this part of the lecture, we're going to talk about the CMOS circuit styles, the static and the dynamic. Okay, so we have two types of CMOS circuit styles, static and dynamic, and mostly this is the most common. The static CMOS is the most common, you can say, and the dynamic configuration or dynamic styles is less used compared to the static part. So what's the difference between a static CMOS and the dynamic CMOS? So static CMOS here means that is the output is connected to either VDD or ground via a low resistance path. So you've seen the inverter before. So if you still remember the inverter, that the NMOS and PMOS can be switched on at the same time, where both are in saturation when VDD when Vin. So if you remember, is Vin is VDD over 2 for the inverter. So for the inverter Vin VDD over 2, we have the NMOS in saturation or velocity saturation, and PMOS also in saturation. So we have a current flow from VDD to the PMOS to the output node, and then from the output node through the NMOS to the ground. So you have a direct path where both transistors are on. So in dynamic CMOS, okay, so in the dynamic CMOS, relies on temporary storage of signal values and the capacitance of high impedance circuit nodes, where no direct path from VDD to ground. Okay, so later on we'll see what's the difference, but basically we cannot have both devices switch on at the same time as compared to the static CMOS. So there's a lot of advantage of the static CMOS. That's why it's most common. Some of it is, for example, here it has a high noise margin, low output impedance with a high input impedance. We don't need a clock here; requires a clock signal. Okay, clock signal here doesn't mean it's a register or sequential circuits. It just means that it requires a special clock signal for it to work. The static CMOS doesn't require the clock signal, but the main thing is steady path between VDD and ground. Okay. So we're going to talk about the most common one, even still in use today, in real circuits. That is the static CMOS. Okay. So when you talk about static CMOS, you have the pull-up network and the pull-down network. So what is the pull-up and what is the pull-down? So I think it's the same as the inverter we've seen already. That the pull-up network is actually trying to pull up the output node F from 0 to VDD, and then the pull-down is pulling down node F from VDD to ground. Okay, so some configuration on the input side, for example, for the inverter, if you put input 0, we are going to pull up, right? So if you put 0 on the input, you're going to pull up F. If you put a logic 1 or VDD on the input, we're going to pull down. Okay, so PUN, PMOS only, PDN NMOS only, PUN, PDN are dual logic networks. Okay, so for pull-up, okay, for pull-up, we are going to use a PMOS device. So here, actually, you want to see, can we actually pull up using an NMOS? So here on the right side here is we are trying to pull up the node F. So here is node F. So what's the difference if you try to pull up using a PMOS and pull up using an NMOS? Okay, so ideally you want to pull up using PMOS because there is no voltage drop. So that's the idea. So if you put a 0 here, so here is your gate, here is your source, your drain, and for the NMOS it's a little bit different. So NMOS, okay, so NMOS you have gate, you have the source down here and the drain up here. Okay, so let's look at the PMOS. So VGS is negative. Okay, so So here you have your VGS is negative, is it on or off? So if you put a 0 here, is on. Okay, so PMOS is on, and now you have current ID flowing through, and it's going to pull up the node F from 0 to VDD. Okay. Okay, so your source, your drain, and it's pulling up 0 to VDD, and then okay, and then for the NMOS side, is it on or is it off? So if you put VDD here, and assuming at t equals to 0, your F is equals to 0. Okay, t equals to 0, F 0. So if F is 0, then you have a positive VGS, so the NMOS is on, and now you have a current flow ID. Okay, and the current ID is trying to charge the node F, trying to charge CL on node F. Okay, so now it's charging. Okay, now it's charging node F until a certain point. It's going to stop charge. So when is it going to stop charge? It's actually going to stop charge when your F, okay, your F is equals to VDD minus VTN. So essentially we can see here that your F max, okay, your F max is only VDD minus VTN, whereas here your F max is VDD, so you have a full swing when you charge it. Okay, so you lose some voltage. So if you basically, you can try to say that if you try to pull up using an NMOS device, you are going to lose VTN. You're going to lose voltage by VTN. Okay, so similarly here in a pull down. So pull down we use an NMOS. Okay, so we have an NMOS here, and if you put VDD here, this is your drain, this is your source. Okay, and so your VGS is greater than VT. Okay, your VGS is positive, greater than VT is on, so it's going to discharge node F here. It's going to discharge from VDD to 0, pulling down, and it's going to pull down all the way to 0. Okay, it's going to pull down all the way to 0, whereas on this side, if you use a PMOS, okay, so if you use a PMOS, your gate is here, so your VGS, okay, your VGS is initially on, so you're going to pull down the voltage, but it's going to pull down only up to VTP. Okay, so here is your F min. Okay, your F min. Okay, so if you pull down using NMOS, you get your swing or your pull down from VDD to 0. But if you try to pull down using a PMOS, you're going to pull down only until the threshold voltage VTP, and it's not going to go down to 0. And that's why we use a NMOS for pulling down and PMOS for pulling up. Okay, the construction of a pull down and a pull up network. So basically, NMOS device in series implement a NAND function, whereas if you put an NMOS in parallel, it implements a NOR function. So let's have a look here. Okay, let's have a look here. So what it means here, so let's say this is node F, and what happens if you put let's make a small truth table here, A, B, and F, and what happens if you put 0? If you put a 0 here, okay, 0 0, so this is off. Okay, so F is going to is equals to 1, basically. It's not pulling down. Okay, similarly, if you put 1 0 0 1, okay, so 0 1 and 1 0 and then 1 1. Okay, so if you put 0 1, again, there's not going to be a path to pull down, so going to maintain VDD, but if you put a 1 here, okay, if you put a 1 and a 1, so this is on, and you have an ID discharge, and it's going to be 0, and this is basically your NAND function. Okay, a NAND function. Okay, so what about the parallel? So in parallel, you can analyze the same. So 0 1 1 0 1 1, and if you put a 0 here and 0 there, it's going to be a 1. Okay, because there is no they cannot pull down to 0. Okay, but if you put a 1 here, okay, and a 0 there, now we have a current going down, and it's going to pull down. So pull down to 0, okay, through B. Okay, and similarly here, if you analyze the same, it's going to pull down through A, and if you put both 1, it's going to pull down, and here is actually your NOR function. Okay, NOR function 0 plus 0 bar. Yeah, okay, so NOR and NAND. Okay, De Morgan's theorem. I think you've seen already the De Morgan's theorem. Maybe in your undergraduate, a parallel connection of transistors PUN correspond to a series connection of the PDN and vice versa due to based on the De Morgan's theorem. So complementary gate is naturally inverting. So if you implement in static CMOS, the best gate is actually a NAND and a NOR. If you need an AND gate, then you need to implement an inverter. Okay, so this is your AND gate. Okay, by default is a NAND and a NOR. Okay, number of transistors for an input logic gate is 2n. We'll see about that. Okay, so here is actually your static CMOS NAND gate. Okay, so let's analyze a little bit. So let's see what happened here is so this is in series. Okay, so series NMOS corresponds to the parallel PMOS. Okay, so we can see that series NMOS corresponds to parallel PMOS. Now what happens if you put 0 on A and B? So A, you put 0, and then we're going to put a 1, 0 also on the B, and here is going to be cut off, and here is on. Let's put a tick here, on and tick. Okay, so what happens if the NMOS is off? So so ID equals to 0. IDN is equals to 0. Okay, so no current to discharge. But here is on, so you're gonna have current IDP. Okay, so that's why you have a logic 1 there. Okay, when you put 0, it's going to basically pull up. Okay, here is equally pull up. So if you do the same analysis, you can see that for example, if you put 1 1, okay, if you imagine if you put 1 1 here, okay, if you put 1 1, this one is off, on. So the NMOS is on, so both NMOS is on, and it's going to discharge the node out, the node F, okay, to ground, and you cannot and we cannot pull up because both of the PMOS are off. Okay. Similarly with the CMOS now, is the same story here. Let's take let's try and take this one. Okay, so A is going to give a 1, B 0, A1, B 0. So which one is off and which one is on? So 0 here is on, here is off. Okay, this is on, this is off. Okay, do we have a path from VDD to out? No path. Okay, so you can say the IDP is equals to 0, and then here we have a path going down, so we have IDN here to pull down. Okay, and pull down is going to give you a 0 on the output. Okay. Okay, so complex CMOS gate. Okay, so how do you design a complex CMOS gate? So here is actually your D plus A, B plus C bar. Okay. Okay, so here we can. The first step is to do the pull down network first. The easiest is to do the pull down network. And remember that if you have a plus, it's going to be parallel pull down. Okay, so that's why you have a. If you see here, your BC here is parallel, and it's going to be in series. Is going to be in series with A. Okay, so B plus C is going to be in series with A. you can see here, okay, and then the whole thing is going to be in parallel, okay, because you have a plus there, okay, so this whole thing will be in parallel plus D. And how do you do the PMOS? So the PMOS is the duality, the complementary, okay, so BC now is series, okay, here we have parallel, and then this guy A and BC now is parallel, okay, and here you have series in the NMOS, and then this whole thing here is now in series, okay, whereas here you can see it's D and the whole thing is in parallel. Okay, so it's a duality. If you have remember that if you have a series in the NMOS, which is corresponds to the AND gate, the AND operation, or the NAND, then you have a parallel in the PMOS. Okay. Okay, so I think that's all on the complex gate design. The next part of the video, we're going to talk about the logic graph.